All right, so this is 9.1, just the general logic of what a significance test is. And right now you don't know, but once you do, this visual I put on the first slide will be hilarious to you. Not going to be able to stop laughing and thinking about how clever it is. All right. There's a bunch of slides today, so we'll see if we get through all of them. So confidence intervals are one of the two most common methods of statistical inference. So again, just drawing conclusions using statistics. And the other is what we're going to talk about today, which is hypothesis tests or significance tests. And these just basically allow us to weigh the evidence in favor of or against a particular claim. So a good analogy for these is it's like a criminal trial, okay? In the United States, in a criminal trial, the onus is on the prosecution to provide enough evidence, we say beyond a reasonable doubt, right, of guilt. But what is it's called the null hypothesis in statistics. But in a criminal trial, it's just what is believed to be true going into the trial about the person on trial. Innocent until proven guilty, right? And so that's kind of analogous to what we do with a significance test. So it's a formal procedure for using observed data to decide between two competing claims. We call them hypotheses. And the claims are statements about the parameters we're investigating. So for us, in this chapter, it's going to be specifically a statement about a proportion that we're trying to figure out. Oh, yeah.
So I just say like that whole spiel.
Yeah. Yeah. It works really well for this. So students that are in mock trial, I think, will find this to make logical sense. But we have two claims. So the one that we assume to be true is called the null hypothesis. So it's H null, H sub 0. And the one we're trying to find evidence for is called the alternative hypothesis. So the null hypothesis is like innocence, and the alternative would be like guilt. You have to prove guilt. You have to show enough evidence for guilt. And just like in a trial, there are only two possible outcomes. What are the possible outcomes for a criminal trial? Guilty, not guilty. Well, notice that that's guilty, not guilty. It's not guilty, innocent, right? Those are two different things. Just because they're not guilty of that crime does not make them an innocent person. It doesn't mean they haven't ever committed any crime in their entire life. It just means they're not guilty of that crime. They're presumed innocent. So I'll give you this is a quick example. So let's say a free throw shooter claims that his long run proportion of free throws is 0.8. So he shoots 80% from the free throw line. So we suspect that they're exaggerating. All right. So our null hypothesis is always the claim, basically. And our alternative is going to look similar, but it's going to be an inequality. The null hypothesis will be an equation. The alternative will be an inequality. So the null hypothesis is his claim that P equals 0.8. The alternative that we're looking for evidence of, we think he's exaggerating, aka translate that to an inequality. We think that P is what? Less than 0.8. And so here's how you would state those two hypotheses. The null hypothesis, P equals 0.8. The alternative is that P is less than 0.8. So we call the alternative hypothesis one-sided if it's what we call a one-sided inequality, so less than or greater than. And it's two-sided if the alternative states that it's different from the null hypothesis. And so when we say different, it's still an inequality, but it's specifically this inequality. It's not equal to. We call it two-sided because it could be less than, it could be greater than. We just want to know if it's different than the null hypothesis. We're not necessarily hypothesizing that it's one side or the other. It's just different. So those two are one-sided alternative in blue. The purple one is a two-sided alternative hypothesis. All right, so let's practice just stating hypotheses. So at the Hawaii Pineapple Company, managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing season. Managers wonder if this change will affect the mean weight of pineapples grown in the field this year. State the appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. So that's the first thing we're going to do is define the parameter of interest. And in this case, it would be mu, which is the true mean weight of pineapples grown at Hawaii Pineapple Co. Is the abbreviation for Hawaii HI? Is that right? Okay. All right, so we have two hypotheses. Our null hypothesis, which is H sub 0, sometimes we call it H naught, N-A-U-G-H-T, very British. Would just be that the pineapples have the same mean weight as last year, right? The null hypothesis is always an equation. It's an equal. So mu equals 31 ounces. Now the alternative we'll get from the context of the problem. And the only context we have is managers wonder if this change will affect the mean weight of pineapples grown. So what do you think that should make our alternative hypothesis? Yeah, there's no indication of one direction or the other. They just really are wondering if there's going to be a different mean weight. So I would make it a two-sided test. Mu is not equal to 31 ounces. So remember that you're always investigating a parameter. So your hypothesis should make a statement about the parameter, which is why I'm using mu and not x bar here. You have to use the correct notation for a parameter. That's it. That's all they wanted us to do in this one was state the hypotheses. So we're done. Okay, so what you do with the hypothesis test, you state your hypotheses, then you're going to take a sample, you're going to get a sample, and it's going to get you what we call a p-value. And we'll talk about how to calculate a p-value, but a p-value is basically a conditional probability. It is how likely you are to get your sample if the null hypothesis were true. So we actually did this at the beginning of I think we did it. We did that hiring discrimination activity, didn't we? Where it was about female pilots or male pilots feeling discriminated against. So when we did that, we assumed that there was no tampering with the hiring process, right? That was our null hypothesis. And then we calculated what's the probability that we would get this many female pilots by random chance. And if that probability is relatively high, then we go, okay, we don't really have evidence to support the claim that there was tampering with the hiring process. If it's really low probability, so if it's really unlikely to happen by a random chance, then that supports your alternative hypothesis, okay? So I'll go through that in a little more detail here. So a player who claims to make 80% of his free throws, so our null hypothesis there, remember, was P equals 0.8, and we thought he was exaggerating. P is actually less than 0.8 is what we think. We ask him to take a random sample of 53 free throws, and it comes out that P hat is 0.64. So right away, just looking at that, is that evidence for our alternative? Does that support the alternative hypothesis? It does. He made way less than 80%, right? So now we want to see, okay, was that just due to random chance? Or is it unlikely that he would randomly shoot 64% on 53 throws if his true shooting percentage is 80%? That's what we're going to look at. So this is evidence against the null hypothesis and in favor of the alternative, but is it convincing or convincing enough? All right, so if we did 400 sets of 50 shots, and in each one we took or calculated the sample proportion of made shots, only 3 sets out of 400 did our shooter make less than or equal to the observed P hat value when his true shooting percentage was 80%. Okay, so this is like an approximate sampling distribution. If his true shooting percentage is 80%, that doesn't mean he's going to shoot exactly 80% every time. He's not going to shoot 40 out of 50 every single set of 50, right? There's going to be some variability. But only 3 out of the 400 did he shoot 64% or less by random chance. All right, so what's 3 out of 400? Oops. 3 out of 400 is about 0.0075. So less than 1%. So the probability, if he actually shoots 80%, the probability that he would randomly shoot 64% on a given set of 50 shots is less than 1%. Do you think that's convincing evidence that he doesn't really shoot 80%? Right, I do too. So I'll talk about how to actually calculate these p-values later, but right now we just want to interpret it. And so a p-value, again, is just a conditional probability. So p is the probability. It's the probability that you get that sample, that p hat, given that H null, the null hypothesis, is true. So how likely are you to get the sample that you got if the null hypothesis were true? All right, so let's do another example where we're actually given a p-value. Calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. And the NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? Researchers decide to perform a test of H null, the mean is 1,300, versus HA, the mean is less than 1,300, where the mean is the true mean daily calcium intake in the population of teenagers. And they asked a random sample of 20 teens to record their food and drink consumption for 1 day. And then they compute the calcium intake for each student. Data analysis reveals that X bar, so our sample mean is 1,198 milligrams with a standard deviation of 411 milligrams. So our sample mean does support the alternative, right? It is below 1,300, but could that just be from random chance? We just happened to get a random sample of 20 teens who were ingesting less than 1,300 milligrams of calcium. Well, they perform a significance test and they get a p-value of 0.1404. All right, so A, explain what it would mean for the null hypothesis to be true in this situation. So if the null hypothesis is true, then the average teenager does take in 1,300 milligrams of calcium a day. B, interpret the p-value and I'm going to say if the null hypothesis, actually I'm going to abbreviate it. If H null is true, there is about a 14% that 14% chance that we would get our sample, which is X bar equals 1,198 milligrams, by random chance. So if teenagers are in fact ingesting 1,300 milligrams of calcium a day, there's about a 14% chance that we would get our sample, which was 1,198 milligrams or less. So is that enough evidence, do you think, to support the alternative hypothesis? Is 14% super unlikely? It's not super unlikely. It's going to happen more than 1 every 10 samples. So no, I would say that's not enough evidence. The lower your p-value, the more evidence you have for your alternative hypothesis. So we're saying if the null hypothesis is true, there's a 14% chance we get our sample or less. Not super unlikely. So I'm going to make a note of that for you. All right, so what's the cutoff? How unlikely does it have to be before you're willing to say this is beyond a reasonable doubt in court, or this is unlikely enough that I'm going to say I don't think the null hypothesis is true. I think I have evidence for the alternative. And so again, the standard in a court case is this kind of nebulous beyond a reasonable doubt. In statistics, we tend to create a threshold before we run the test. So if it's below this, I'm going to say I have enough evidence. If it's above this, I'm going to say I don't have enough evidence. So this is where this little joke comes from. It's not really a joke. It's actually mostly true. But usually below 5%, so 0.05, is deemed as significant. But again, you're going to make that decision before you run the test. And that's called the significance level of the test. All right, so we call the significance level alpha. And that's your boundary for deciding whether an observed result is unlikely to happen by chance alone when the null hypothesis is true. When your p-value is less than alpha, we say the result is statistically significant at the alpha equals whatever you set alpha to level. Alpha should be stated before you go out and collect data. You should decide on that significance level first, otherwise that's generally unethical statistics because you can just set your alpha to be bigger than what your p-value is and go, boom, I have a statistically significant result. But the decision on what alpha needs to be is pretty complicated. You guys won't have to make that decision. You'll be told. Run the significance test at the alpha equals 0.05 level or whatever. All right. Generally, yeah, the most common alpha level is 5%. So you'll be using that quite a bit. If it's not stated for you, just default to alpha equals 0.05. 99% of the time it'll be stated for you. But you'll see alpha equals 0.05 or alpha equals 0.01. And sometimes alpha can be as big as 0.1, although not super common. All right. So let's just practice drawing conclusions from a significance test. So here we're testing batteries, and what we want to do is figure out what the true mean value of battery life is. So we took a simple random sample of 15 AAA batteries and use them continuously until they're completely drained, and the sample mean lifetime, our X bar, is 33.93 hours. And then we run a significance test using the null hypothesis that the mean is 30 and the alternative that the mean is greater than 30, right? Which our sample does seem to support. Our sample mean was larger than 30. So we run that test and we get a p-value of 0.0717. What conclusion would we make at the 0.05 level? All right, so just like in a criminal court case, there are two possible conclusions. In a criminal court, it's either guilty or it's not guilty. Same deal with hypotheses tests. Notice that both of the criminal outcomes are given in terms of guilt. So both of the outcomes for us are going to be given in terms of the alternative hypothesis. We either have enough evidence to reject the null hypothesis in favor of the alternative, or we don't have enough evidence to reject the null hypothesis in favor of the alternative. All right, in this case, is our p-value bigger or smaller than our significance level? It's bigger. When it's bigger, that means that it is likely to have occurred by chance, meaning it's not unlikely enough. We don't have enough evidence to say that this didn't occur by random chance. So when this is larger than our significance level, we fail to reject the null hypothesis. We're saying, okay, this could have just occurred by random chance. It doesn't mean that our alternative is necessarily true. So the way we're going to state it is we fail to reject H null in favor of HA at the alpha equals 0.05 significance level. We don't have sufficient evidence that the true mean battery life is greater than 30 hours. And so generally, it's kind of a scripted deal. For a significance test, the conclusion should be 2 sentences. In the first sentence, you're going to abstractly just make the statement, the declaration, whether you do reject or fail to reject the null hypothesis in favor of the alternative. The second sentence, you add context. So you kind of restate it, but in the context of whatever you're studying. So we were studying battery life of HA. All right. So just like in a criminal trial, the defendant is never proclaimed innocent. They're either guilty or not guilty. We're never proclaiming anything about the null hypothesis. We're never accepting the null hypothesis. We're either rejecting it or we're failing to reject it. All right, and so this is the exam tip I just gave you. So your first sentence gives your decision about the null hypothesis, either reject or fail to reject. And the second sentence provides a statement about whether or not there is convincing evidence for the alternative in context. So just adding that context. All right. So we're getting towards the end here. The last thing we're going to talk about is errors. And so when I talk about errors here, I'm not talking about you, the statistician, are making some clerical error or anything like that. But even if we reject the null hypothesis, so our significance level is, or our p-value is below our significance level, and I could go, hey, look, I have good evidence that this didn't happen by chance. So I have evidence supporting my alternative hypothesis. There's always the issue that, well, it could have happened by chance, right? And I just made the wrong decision. I just got this really unlikely sample that supported my evidence, but it just happened that way, right? That's an error, right? So there are 2 types of error. There are the error where you reject the null hypothesis when you really shouldn't have, and then there's the other direction. You fail to reject the null hypothesis when you really should have rejected the null hypothesis. So just like the errors that can happen in a court trial, right? In a criminal trial, you could convict an innocent person, or you could fail to convict a guilty person. Which one's worse? Oh, Sam just made a decision on that. It's like the ethics question, right? Where the, what is it? The person laying on, do you guys know that? The trolley problem, where there's a person laying on the track at a switch.
There's like, do you kill your one family member or like 5 people you don't?
Well, you could not intervene and it's going to kill it's going to kill 5 people, right? Or you could intervene, switch the track, save 5 people, but it's going to kill 1 person.
Yeah.
But in that case, you are killing that person.
Uh-huh.
In the other case, you kind of don't have blood on your hands because you're not intervening at all.
Right.
So my point of this is there's not really a good answer one way or the other. It kind of depends on the crime, right? And that's the same. What's worse, type 1 or type 2 error? Well, depends on the context of the problem. So let's talk about what they are. So type 1 occurs if a test rejects the null hypothesis when actually the null hypothesis is true. So you can think of this as a false positive. I got new slides for this new text. I should have included, I had inserted, or hold on, I'll see if I can show you while you're writing this down. All right. So this is a type 1 error. It's a false positive. And this is a type 2 error, which is a false negative. So it's incorrectly failing to reject the null hypothesis when the alternative is true. Yeah. The exact opposite of what I just told you. This is not a human error. This is. So yeah, type 2 is false negative. You failed to reject the null hypothesis when you should have rejected the null hypothesis because the alternative is true. All right. So let's talk about errors that could happen, and then we'll decide whether in this context a type 1 or a type 2 is worse. So a potato chip producer and its main supplier agree that the shipment of potatoes must meet certain quality standards. If the producer determines that there are more than 8% of potatoes in the shipment have blemishes, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips, and to make a decision, a supervisor will inspect a random sample of 500 potatoes from the shipment and then perform a test at the 5% significance level of P equals 0.08 and P is greater than 0.08. When P equals the true proportion of potatoes with blemishes in a given truckload. Describe a type 1 and a type 2 error in this setting. All right, so type 1 is a false positive. So remember, false positive, and positive in the case of a hypothesis test is saying we have evidence for the alternative, right? So this would be incorrectly rejecting H null in favor of HA and sending the potatoes back. So this would be the chip producer saying, hey, these aren't good enough potatoes. Go get me a new batch. When in reality, they are good potatoes. Does that make sense? So kind of wasting a truckload of good potatoes. All right, type 2. That's going to be our opposite, right? So that's our false negative. And that would be incorrectly failing to reject H null. And so to give you context, that would be kind of keeping a truckload of over blemished potatoes. When they have like sprouts. What's worse in this context?
I feel like we need more information.
Yeah.
What happens if the potatoes are blemished? Like, is that bad? Or
I know, this one's kind of hard to make a decision on because if it's just aesthetics,
Then, like,
then probably wasting a truckload is worse, right?
Right.
Type 1 is worse. But
But if someone gets sick. then they
yeah,
have
if
to
it's like if blemished potatoes are bad for you, then you wouldn't want. Then type 2 is worse, keeping bad potatoes. So they say in our text, they're saying that type 2 is worse just because more potato chips are made with blemished potatoes, which could upset customers.
the potato chips display what the potato. I feel like you wouldn't know. Maybe I'm crazy, but I feel like if you got a potato chip, you wouldn't necessarily know what the original potato
Well,
was.
sometimes you get those like brown,
If it's
Yeah.
but that's overcooking. I don't think that has anything to do with the aesthetics of the actual potato.
I think they're being very wasteful.
Yeah, this is food waste and capitalism at its worst.
Yeah, totally. Yeah.
All right. So your significance level is going to be adjusted based off of whether you think a type 1 or type 2 error is worse. The probability of a type 1 error is equal to your significance level, whatever you set it to. It's equal to alpha. So if a type 1 error is bad and you don't want to commit that, then you would just set your significance level to be really low. Make it really unlikely that you would commit a type 1 error. So really unlikely that you get a false positive. The probability of type 1 is alpha. We can decrease the probability of a type 1 error by decreasing the significance level. But there's a trade-off between type 1 and type 2. So when you decrease the probability of committing a type 1, you're increasing the probability that you commit a type 2 error. All right, so that's it. That's our basics of significance tests and how to interpret p-value and how to draw conclusions from the p-value. If the p-value is below alpha, you reject the null hypothesis in favor of the alternative. If it's above alpha, you fail to reject in favor of the alternative. Your problem set, I put it in this week's module. It's just what I've started doing, so it's not problems from the book. It's just more like the formative assessment style problems, so a little shorter, but more similar to free response type problems that you're going to see on my exams and the AP exams. All right, I've also assigned, because we finished chapter 8